Now let me show you a really helpful use of this that's really fast. What if I want to take the number, I don't know, 1 plus, let's go 1 minus I, 1 minus I, and I want to raise it to, say, the fourth. Okay? Now, this isn't a terribly difficult thing to do, right? I mean, if I had to, I could go 1 minus I times 1 minus I, or I could use Pascal's triangle, which maybe we'll do at the end just for giggles, 1 minus I, right? However, watch. Here's what I'm going to do. I'm going to show you how cool this is. I'm going to rewrite, I'm going to let z equal 1 minus I. Okay? I'm just going to let z equal that. Now, if you think about this in terms of the complex plane, so here's my real and here's my imaginary. If I go over 1 and down 1, right, doesn't this point right here represent 1 minus I? True? Now, let's think about this. What angle measure is this? If I go over 1 and down 1, isn't this angle, if I had to, I could do all kinds of nasty stuff. Remember that tangent of theta equals y over x. So if I had to, I could do it that way, but this is a relatively simple problem. Can't you see that this theta is just equal to negative pi fourths, right? Theta is equal to negative pi fourths. So all that I need, remember, any x plus yi can be written as r times cosine of theta plus I sine of theta. So all I'm going to do is I'm going to figure out how long this guy is. Remember how this worked? I need to know this radius, which is really just the modulus, which in this case is, remember, r and the modulus of z are basically the same thing. They're the radius that got us from the origin down to the point. I know that z is equal to 1 squared plus negative 1 squared, which is equal to, well, pardon me, take my square root of that, right, which is equal to the square root of 2. Okay? So, and we got to be a little bit careful here. I'm going to let's keep everything in mind because this can get kind of crazy in just a sec. I can rewrite this as root 2 times cosine of what? Times the cosine of negative pi fourths. Remember, that's what theta was over here. Plus root 2 times I times the sine of negative pi fourths. Let's give ourselves a little bit of space right there. True? Now, if I needed to prove that, I could plug it back in. I know that the cosine of negative pi fourths is root 2 over 2. Root 2 times root 2 over 2 is 1. That's x. I know that the sine of negative pi fourths is negative root 2 over 2, right? 2 times negative root 2 divided by 2 is negative 1, which is y. And then, of course, the I is just along for the ride. So if I wanted to rewrite this, I could write this as root 2 times the cosine of negative pi fourths plus I sine of negative pi fourths. Or if I want to be fancy and use a new notation, I can write this as root 2 cis negative pi fourths. Okay? So I'm not, though. I'm gonna rewrite this as, so I know that z is equal to root 2 times the cosine of negative pi fourths plus I sine of negative pi fourths. Right? Now again, you always want to keep your eye on the prize as far as what quadrant you're in. All right? Just be really careful. I know that 1 negative 1 gets me into the fourth quadrant in the complex plane, right? So I want to make sure that I get values that are making sense. The sine of negative pi fourths is going to be negative, which is what I want. So you always kind of want to be double checking along the way. So what did I say? I know that this also equals 1 minus I. So if I want to do 1 minus I to the fourth, then really all I'm looking for is, what is z to the fourth? Well, what is z to the fourth? According to DeMoivre, I take root 2 and raise it to the fourth, and then I multiply cosine of negative pi fourths times 4, right, plus I sine of negative pi fourths times 4. Lost my dingle. Now watch what happens. What's root 2 to the fourth? Well, root 2 squared is 2, so root 2 to the fourth has to be 4. What's This ends up being cosine of negative pi plus I sine of negative pi. Remember, these two angles always have to be the same. They've always got to be the same thing. So let's see, what's the cosine of negative pi? Well, if you had to do it, right? I know that, think about this. Cosine of pi is -1. Cosine of negative pi is -1 as well, right? So this ends up being 4 times -1 plus, what's the sine of negative pi? Well, that's easy. Sine of 0 is 0. Sine of negative, because they're 2 pi away from one another. That's another way to think about it. Excuse me. So this ends up being 0, and guess what? My answer's -4. Yeah, isn't that awesome? That is so cool. Now, wait, let's do one where it's not as pretty. Okay, let's do, I don't know, let's go x plus 2. No, let's do, sorry, x, that's crazy. I want to do, let's go 1 minus or plus 2i. Let's go 1 plus 2i, and let's raise it to the 5th. Now this one's not going to be as pretty because the numbers aren't going to work out the same way. So let's just double check. Let's figure out where we're at. I'm over 1 and I'm up 2. So I'm in the first quadrant, right? Because this, again, this is the real, this is the imaginary. I go over 1, I go up 2. So this point is, this is going to be ours, the length of this is going to be modulus z, right? And this is going to be 1 plus 2i. Now, what's the first thing that we need to do? The first thing that we need to do is rewrite this guy. I want to take 1 plus 2i, and I want to rewrite it. So I'm going to take 1 plus 2i, and I'm going to turn it into an r times cosine of theta plus I sine of theta. That's what I want to do first. So I need to figure out what r is. I need to figure out how long that thing is. So I know that r is equal to the square root of 1 squared plus 2 squared, affectionately known as the square root of 5. Right? Easy peasy. Now I need to find theta is the only problem. That makes me a little bit nervous. So how am I going to do this? Well, what do I know? Remember, this is an x and this is a y. And I know that the tangent of theta per the polar coordinates is always y over x, which implies that tangent of theta equals 2/1. It's a theta, by the way, which implies that theta equals the inverse tan of 2. I don't have to worry about, remember, the inverse tan only spits out values. My spidey sense tingles from negative pi halves to pi halves. So I don't have to worry about it because I'm in pi halves, right? I'm in that interval. So I'm going to crank over to my calculator. Ooh, look at that. Second quit. And let's see let's keep it in degrees, shall we? Let's go to mode. I'm going to go down to degrees. Just so because otherwise I'm going to get really strange numbers that I'm not, it's hard to wrap your brain around what, I don't know, 2.8 is for a radian measure. So we'll keep it in degrees, and we'll leave it in degrees for the rest of the problem. Excuse me. So I'm going to go second tan, or inverse tan, of 2. Let's see what we get. I better end up in the first quadrant. Look at that, 63.435 degrees. I'm going to cheat just the smallest bit. I know you guys are going to yell at me. It's okay. I'm going to round to the whole degree on this. Please round to whatever I ask you to round. All right, so look at what we have here. I know that theta is equal to, approximately equal to, hee little cheater, 63 degrees, as opposed to 60 degrees. What is wrong with me? At 63 degrees, right? Which implies, you ready? Here we go. This is the fun part. I know that 1 plus 2i can be written as the square root of 5 times the cosine of 63 degrees plus I sine of 63 degrees, right? Remember that little move we did? Here's the coolest part. Once I got this, this implies that 1 plus, oh, if you want to get fancy, I could write this as root 5 cis 63 degrees. If you're going to write in degrees, keep it, you've got to include this unit. Remember, that's the point. If it's going to be in radians, it has no unit. So if you write it as cis 63, then it means that it's 63 radians, which is a whole different deal. Okay? So if I'm going to do 1 plus 2i raised to the 5th, what's this equal to? It's going to be root 5 raised to the fifth, bunch of 5s flopping around, right, times the cosine of 63 degrees times 5 plus I sine of 63 degrees times 5, right? Now let's see, think about this. What do we got? We got 5 square, root 5 squared is 5, so root 5 to the fifth would be what, 25 root 5? 25 root 5 times cosine of what? Well, 5 times 60 is 300, 5 times 3 is 15, so it's about 315. This is going to be cos 315 degrees plus I sine of 315 degrees. Or if I want to get fancy, I can write 25 root 5 cis 315 degrees. Powerful good loving. That's some good stuff. Okay, cool. That's a really cool application of DeMoivre's. Okay, so we have DeMoivre's, right? Which we know that if I take z to the n, it equals r to the n times cosine of n theta plus I sine of n theta. We just use this to great effect up here. Just a quick little refresher. We know what we're doing, right? What, pray tell, I mean, if n is a whole number, we're golden. But what happens if I want to say take the nth root of z? You know what I mean? What if I want to take, say, now I'm going to do an example directly from the book. You can follow this. This is on page 579, and this is going to be example number 6. Okay? What if I want to take, if I want to find all of the complex cube roots, the complex cube roots, where's -3 coming from? Sorry, of, say, -1 plus 3i. Okay, now I don't know what you remember from your algebra, but if I've got a cube root of any thing, basically there are 3 solutions. They may all be real solutions, they may all be imaginary solutions, or they may be a combination of both. Okay, but what I want to do is I want to be able to figure out the nth root of something. Now, I'm going to give you a formula. We'll revisit this in just a sec. I'm going to give you a formula that's going to make you feel like running for the hills. It's not running through the hills. That'd just be fun. This one's not so much fun. And then we're going to apply it, okay? But I don't want you to panic when you see this, because, okay, check it out. This is going to say z sub k is equal to the nth root of r. Now, that smells real similar to what we did here, right? But I know this looks frightening. It's like, what the heck is this k thing? Well, I'll describe that here in just a sec. Times the cosine of theta naught divided by n plus 2k pi over n plus I sine of theta naught divided by n plus 2k pi divided by n. Now, what is n? That's easy. That's the nth root. So in this case, n is going to be 3. And you really want to take that time to identify all these crazy variables, okay? However, what is this k thing? Well, k is easy. It's just 0, 1, 2, 3, ... up to n minus 1. And I'll describe what's going to happen here. All right, so I'm going to click over here and I'm going to rewrite the formula, and then I'm going to show you how to use it on that one problem. So z sub k is equal to the nth root of r times cosine of theta naught. We're not afraid of this theta naught notation, right? Theta naught over n plus 2 pi k over n plus I sine of theta naught over n plus 2 pi k over n. All right, this is the angle measure. Excuse me, right there. Now, what did we say? We're gonna find all complex. Now remember, complex roots include real numbers. Complex does not imply imaginary automatically. Complex values are of the form, or complex numbers are of the form x plus yi. So if it's a real number, that just means that y, the y coefficient, is just 0. Okay, find all complex roots of, and we're going to do -1 plus root 3i.